Usually when we think about the fundamental building blocks of the universe, there's this underlying expectation of solid, unyielding precision.
Right, like architecture.
Exactly. Like you look at a brick wall, you see the individual bricks. And the physicist just points to an atom and then a proton, then a quark, and says, well, there it is.
That's the smallest dot of reality.
Yeah, the final indivisible speck.
It is deeply comforting to imagine the universe that way, honestly. I mean, we are macroscopic creatures.
Right. We like our reality to be visible.
Exactly. To be categorized into neat, tiny little points that we can track and measure and just put into a box. A dot or not a dot. Binary. Finite.
But then you step into the world of quantum gravity.
Right.
And the deepest, most hidden layers of theoretical physics. And suddenly, that microscope just shatters.
It really does. We are looking at a fundamental landscape that is, honestly, beautifully murky.
It's no longer a universe of hard, jagged dots. It's a universe of music.
The absolute definition of a cosmic symphony, playing out in dimensions we can't even see.
Orchestrating the very fabric of space and time through this continuous flowing vibration.
Yeah.
Today on Decode in the Dark, we are going to learn how to hear that music.
We really are.
We are going to drift through string theory, M theory, the mind-bending concept of a holographic universe, and the endless landscapes of cosmic possibilities.
It's a beautiful journey.
Welcome to this deep dive. I want to invite you, the listener, to just take a deep breath right now, settle in, and let go of the day's tension.
Just relax.
And please consider liking and subscribing to the channel if you enjoy our journeys together. This particular deep dive is designed specifically for relaxing, for winding down, and for gently exploring the greatest mysteries of the universe.
No prior knowledge needed at all.
Exactly. We are guided today by a really fascinating stack of sources. We've got research papers, academic articles, and these sweeping historical overviews of quantum gravity.
And we've taken all of that incredibly dense mathematics and distilled it down
into its most mind-expanding, peaceful concepts. Our mission is to unravel the ultimate fabric of reality, transforming complex, invisible dimensions into a beautiful cosmic symphony that will gently rock your mind to rest.
I love that.
Okay, so let's unpack this.
Let's begin at the very foundation of matter, because we need to understand why physicists ever felt the need to abandon the idea of those comfortable little dots in the first place.
Right.
For a long time, traditional quantum field theory treated the fundamental particles, like electrons or quarks, as zero-dimensional points.
Which is hard to even picture.
It is. If you try to imagine a geometric dot with no length, no width, and no height, you are imagining a mathematical abstraction. It takes up literally zero space.
Just a harsh, infinitely small speck of existence, like the singularity of matter.
Exactly, and for decades, that model worked beautifully. It gave us the framework to explain three of the fundamental forces of nature.
The strong nuclear force, the weak nuclear force, and electromagnetism.
Right. It culminated in the standard model of particle physics, which is arguably, the most successful scientific theory in human history, but it harbored a dark mathematical secret.
The forces didn't want to play together.
Well, one specific force refused to join the quantum party.
Gravity.
Yeah, gravity. When physicists tried to invite the fourth fundamental force into this zero-dimensional quantum framework, the mathematics just completely exploded.
Because gravity, at least as described by Einstein's general relativity, is all about a smooth, continuous curving fabric of space-time.
Right, it's like a beautifully stretched trampoline.
Yeah, heavy bowling balls warp it gently, and marbles roll around the curves. But quantum mechanics is the exact opposite.
It is jittery. It is discrete.
It's a bubbling, chaotic quantum foam at the smallest scales.
So to merge the two, physicists hypothesized a quantum particle for gravity. They called it the graviton.
And following the rules of quantum field theory, they treated the graviton as a zero-dimensional point particle.
Exactly. And the disaster happens when you try to calculate the interaction between two of these gravitons.
What happens?
Well, when two zero-dimensional point particles approach each other and collide, the distance between them shrinks to absolute zero.
And even high school algebra tells us that dividing by zero is a terrible idea.
It really is. The mathematical term for this catastrophe is a UV divergence. Because the distance is zero, the gravitational force between them and the energy of that interaction just skyrockets to infinity.
Wow.
Yeah, the calculations yield infinite probabilities, which is physical nonsense.
Right, because you cannot have a 200% chance, let alone an infinite percent chance of an event occurring.
Exactly. The theoretical framework simply breaks down. It produces chaotic, impossible collisions.
Now, physicists had encountered infinities before, right, with electromagnetism.
Yeah.
But they used a mathematical trick to sort of sweep those under the rug.
They used a process called renormalization. It's essentially a highly sophisticated way of subtracting infinities from infinities to leave behind a finite, measurable, real-world answer.
And miraculously, that works for electromagnetism.
It does. It works for the nuclear forces too. But gravity is different.
Why?
Because gravity's coupling constant, which is the measure of its strength, is tied to energy. Because energy and mass are equivalent in relativity.
Right, E equals mc squared.
Exactly. So the closer those gravitons get, the higher the energy, which makes the gravity stronger, which creates more energy, which makes the gravity even stronger.
Oh, I see. It is a runaway feedback loop.
A total runaway loop. Gravity stubbornly refused to be renormalized.
So if the math breaks when the particles get infinitely close, you have to find a way to stop them from getting infinitely close in the first place.
That's the key. You have to completely reimagine the building blocks.
You have to transition from the harsh infinite points to something softer, something continuous.
Something that takes up actual space. And that is exactly where the string comes in.
Moving from 0 dimensions to 1 dimension.
It sounds like a tiny conceptual step, but it revolutionizes the entire universe.
Think of a violin or a guitar. When you look at a single guitar string, it is just one physical object. It's a length of wire.
Right.
But depending on how you pluck it, how it vibrates, how much tension is on it, that one single string can play an A, a C, an E.
It can manifest as entirely different notes,
creating entirely different experiences for the listener.
That analogy translates perfectly to the mathematics of string theory. In this framework, an electron is not a fundamentally different object from a quark or a photon.
The universe is not a bucket filled with 50 different kinds of microscopic Lego bricks.
Exactly. There is only one kind of fundamental building block: the string.
So wait, the only difference between the matter making up my hand and the light shining from my desk lamp is the resonant frequency of these fundamental strings.
That's it. Every particle we observe is just a different harmonic of the exact same kind of vibrating stream.
That is beautiful.
One vibrational pattern sounds the note of an electron. Another pattern sounds the note of a quark. And because these strings are one-dimensional, because they have a little bit of length, they instantly solve the gravity problem.
Because they can never collide at a distance of absolute 0.
Exactly. Imagine two geometric points colliding. The interaction happens at a single, infinitely small location in space and time.
Which creates the infinity problem.
Right. Now imagine two one-dimensional strings colliding. Let's say two loop-shaped strings.
Okay, picture two little rubber bands.
Yeah, as they move toward each other and merge, they form a shape that looks sort of like a pair of pants, two legs coming in, merging into one waist.
Oh, I can visualize that.
There is no single sharp point of interaction. The collision is smeared out over the length of the string and over the smooth, curving surface of that pair of pants geometry.
So it smooths out the jittery, chaotic quantum foam.
It does. The distance never drops to 0, the energy never spikes to infinity, and the UV divergences simply vanish.
What's really fascinating here from the sources is that this simple shift from a dot to a line accidentally provided the very thing physicists had been searching for.
Yeah, string theory didn't actually set out to find gravity at all.
It didn't.
No, it was originally studied in the late 1960s to explain the strong nuclear force. Physicists were looking at how particles called hadrons interacted.
And they noticed the math perfectly matched a formula created by Leonhard Euler centuries earlier. A formula that described vibrating strings.
But the theory had a major flaw. As they kept working the math, it kept predicting a particle that they didn't want.
Like an unwanted guest.
Exactly. The equations demanded the existence of a specific vibrational mode, a massless particle with a quantum property called spin 2.
And in the context of the strong nuclear force, that made no sense.
None. The strong force doesn't have a massless spin 2 particle. For a few years, this was considered a fatal bug. String theory was largely abandoned.
But then, in 1974, a couple of physicists, Joel Shirk and John Schwartz, took a second look at that annoying, unwanted spin 2 particle.
And they realized it wasn't a bug, it was the ultimate feature.
Oh, wow.
They recognized that a massless spin 2 particle is the exact theoretical profile of the elusive graviton.
The fundamental carrier of the gravitational force.
Right. Without even trying, string theory had naturally inevitably produced a quantum theory of gravity.
It's like trying to invent a new kind of glue for wood, failing and accidentally discovering the recipe for the stars.
That's a great way to put it.
And diving into our sources, I see that these strings come in two different topologies or shapes.
Yes, there are open strings, which are like tiny wiggling line segments with two distinct ends.
Okay.
And there are closed strings, which are perfect little loops, like those microscopic rubber bands we talked about.
And that distinction is incredibly important for the architecture of the universe, right?
It is. Open strings have endpoints. These endpoints act like anchors. They can attach to surfaces or other structures in higher dimensions.
And the vibrations of these open strings correspond to the particles that carry the nuclear and electromagnetic forces.
Right, the forces that bind matter together, the gauge fields.
The forces that are sort of trapped in our everyday experience.
Exactly. But closed strings, those perfect continuous loops, they have no endpoints. They cannot be tethered to anything.
They are completely free to drift.
And the mathematics shows that the graviton, that massless spin 2 particle, is always a closed string.
Which beautifully explains why gravity is so different from the other forces, why it isn't confined, why it reaches across the vastness of the cosmos, pulling galaxies together.
Because it is untethered.
It's a very soothing image, really. Just imagine, for you listening, at the absolute core of your body, at the core of the device you're listening to this on, at the core of the distant stars, there are no hard, jagged dots.
Just a chorus of unimaginably tiny strings.
Humming a quiet, continuous chord that brings the universe into existence.
The ultimate cosmic symphony.
But, a symphony requires a medium. It requires space.
Right. To understand this music fully, we have to look at the acoustics of the room it's being played in.
So if the strings are the instruments, what is the concert hall? And this is where the theory takes a turn from the beautiful into the mathematically bizarre.
The hidden dimensions.
Yeah. To remain mathematically consistent, to keep those infinities at bay, string theory requires a very specific and very large stage.
It does?
And I have to express some genuine skepticism here, because this is the point where a lot of people feel like theoretical physics loses its grip on reality.
It's a common feeling, yeah.
I mean, you and I, and everyone listening, we live in a three-dimensional spatial world. We can move up and down, left and right, forward and backward.
And we move through one dimension of time.
That's 4 dimensions total. It's obvious, it's intuitive, it's what our brains are wired to perceive. But the sources state that string theory requires 10 or even 26 dimensions.
Yes, 26 originally.
Where are they? Is this just a case of physicists inventing imaginary spaces to force their equations to work out?
The skepticism is completely justified, honestly. It feels like mathematical sleight of hand. But physicists aren't just making these dimensions up out of thin air to cover their tracks.
So where do they come from?
The mathematics of the quantum world absolutely forces these extra dimensions upon us. If we don't include them, the theory predicts physical impossibilities. It fundamentally breaks down.
Let's trace the causality of that breakdown. Why does a vibrating string demand more room to vibrate?
It comes down to something called the world sheet.
The world sheet.
Yeah, when a zero-dimensional point particle moves through space and time, it traces out a one-dimensional line. Think of a pencil point drawing a line on a piece of paper. We call that a world line.
Okay, makes sense.
But a string is already a one-dimensional line. So when a string moves through time, it sweeps out a two-dimensional surface.
Like dipping a wire wand into a bucket of soapy water and pulling it through the air.
Perfect analogy.
As you pull the one-dimensional wire, it leaves behind a shimmering two-dimensional soap film.
That shimmering soap film is called the Polyakov action, or the world sheet. It is the history of the string's movement through space-time.
Wow.
Now, to make string theory a true quantum theory, physicists have to quantize this world sheet. They have to apply the jittery, fluctuating rules of quantum mechanics to that shimmering soap film.
Because at the quantum level, nothing is perfectly still. The soap film is boiling with quantum fluctuations.
Exactly. And when you calculate those quantum fluctuations, you run into a massive mathematical hurdle called the Weyl anomaly.
The Weyl anomaly.
Right. Without getting bogged down in the deepest equations, the act of quantizing the world sheet introduces mathematical artifacts into the system. These artifacts are called the Faddeev-Popov-BC ghost system.
Ghost fields. Physicists really have a knack for coming up with terrifying, esoteric names for mathematical balancing errors, don't they?
They certainly make the math sound more dramatic, but a ghost in this context just refers to a state with a negative probability.
Which is, again, physical nonsense.
Right.
I mean, I can have a 50% chance of flipping a coin and getting heads. I cannot have a negative 50% chance of getting heads.
The math of the original version of the theory, called bosonic string theory, generates these ghost fields, and they contribute a specific mathematical value to the system called a central charge.
Okay.
The ghost fields produce a central charge of -26.
So the system is out of balance by -26.
Exactly. For the theory to be anomaly-free, for it to make logical sense and not produce these impossible negative probabilities, the total central charge of the entire system must perfectly balance out to 0.
So the -26 must be canceled out by a +26?
Yes.
And where does that positive value come from?
It comes from the dimensions of space-time itself. In bosonic string theory, every dimension of space-time that the string moves through contributes a central charge of +1 to the world sheet.
Oh, wow.
Therefore, to cancel the -26 from the ghost fields, the string must vibrate in exactly 26 dimensions.
It's not an arbitrary choice at all, then.
Not at all. It is yes, supersymmetry proposes a deep underlying harmony in nature. It suggests that every force particle, every boson, has a corresponding matter particle, a fermion, and vice versa.
It's a perfect symmetrical balancing of the cosmic scales.
And when you inject this supersymmetry into the equations, bosonic string theory evolves into superstring theory.
How does this new upgraded theory handle the 26-dimension problem? Does it change the math of the ghosts?
It changes it entirely. When you include the world sheet fermions and their corresponding superghost partners, the total negative central charge generated by the anomalies drops significantly.
Down to what?
It goes from -26 down to -15.
Okay, well, that's a much more manageable deficit.
It is. Furthermore, in superstring theory, each dimension of space, along with its fermionic partner, contributes a central charge of +1.5 rather than just 1.
So to cancel out the -15, you simply divide 15 by 1.5.
And the result is 10.
The mathematics perfectly and unyieldingly demands a 10-dimensional universe, 9 dimensions of space and 1 dimension of time.
Exactly. And this supersymmetry also magically fixed another massive headache, the tachyon.
The tachyon.
Yeah, the tachyon was a hypothetical particle predicted by the old 26-dimensional theory that had a negative mass squared.
Which meant it would always travel faster than the speed of light.
Right, which would violate causality and completely destabilize the quantum vacuum.
But supersymmetry naturally eliminates the tachyon from the equations.
It does. Superstring theory is clean, it is stable, and it naturally incorporates all forms of matter and all fundamental forces.
It really is a mathematical triumph. But, we still haven't answered the most pressing, grounded question.
Which is?
If the universe requires 9 spatial dimensions to function, why on Earth do we only experience 3?
To visualize this, we need to completely abandon the classic ant on a garden hose analogy that you hear so often. It's too simplistic.
Okay, what should we imagine instead?
Imagine a high thread count bedsheet. If you stand across the bedroom and look at the bedsheet, it appears to be a perfectly flat 2-dimensional surface. It has length and it has width.
Smooth, unbroken, and flat.
Right. But if you take a magnifying glass and get incredibly close to the fabric, you realize that at every single microscopic point on that 2D surface, there are actual 3-dimensional threads looping over and under each other.
So the third dimension is there, but it is tightly woven, curled up, and confined to a microscopic scale.
Exactly. It's compactified, it exists everywhere, but it's too small to traverse unless you are the size of a thread.
So in string theory, the 3 spatial dimensions we experience, up, down, left, right, forward, backward, those are the long extended dimensions.
They are the flat surface of the bedsheet, but the other 6 spatial dimensions are compactified.
Curled up into unimaginably small, complex geometric shapes.
That exists at literally every single point in our visible 3-dimensional space.
I just want to pause and let that visual sink in for you, the listener. As you wave your hand through the empty air right now, your hand is not just moving through a 3-dimensional void.
It is sweeping through trillions of microscopic, curled up, 6-dimensional shapes that are woven into the very fabric of the air itself.
That is just incredible to picture. These shapes have a specific mathematical name, right?
They do. They're known as Calabi-Yau manifolds. Named after the mathematicians Eugenio Calabi and Xing-Tum Yau. They actually studied their properties before string theory even needed them.
What do these Calabi-Yau spaces actually look like?
They are incredibly intricate, beautiful, folded geometries. Imagine a shape twisted back on itself, with multiple holes, loops, and intersections existing purely in 6 dimensions.
Wow.
They are so complex that the human brain, which evolved to hunt and gather in 3 dimensions, simply cannot fully visualize them, We can only project 3D shadows of them using computers,
And they are tiny, down near the Planck scale, which is 10 to the negative 33 centimeters.
which explains why we can't see them. Even our most powerful particle accelerators, like the Large Hadron Collider in Geneva, operate at energies far too low to probe spaces that small.
So the extra dimensions are safely hidden in the microscopic weave of spacetime. But they aren't just sitting there passively. The geometry of these Calabi-Yau shapes is the secret code of the universe, isn't it?
It absolutely is, because if the fundamental strings are vibrating inside these tiny six-dimensional concert halls, the shape of the hall dictates the acoustics.
The architecture dictates the music.
The exact geometry, the twists, the turns, the number of holes in the Calabi-Yau manifold determines the possible resonant frequencies of the strings vibrating inside it.
And since we established that the vibration of the string dictates the properties of the particle, whether it's a heavy top quark or a lightweight electron or a photon of light.
Exactly. The shape of these hidden dimensions essentially programs the macroscopic laws of physics in our extended three-dimensional world.
So the mass of an electron, the exact strength of gravity, the magnetic charge of a particle, all of the constants of nature that allow chemistry and life to exist are just echoes.
They are the acoustic resonance of the geometry of the hidden six dimensions.
It's staggering to contemplate. The macroscopic cosmos is just a reflection of microscopic geometry.
It really is beautiful.
But as elegant and unified as 10-dimensional superstring theory sounded, the physics community soon hit a massive philosophical wall.
They did. By the mid-1990s, physicists had a crisis on their hands.
They didn't just find one elegant 10-dimensional equation that explained the universe, they found 5.
Yes. The field found itself suffering from an embarrassment of riches, which in theoretical physics is just as bad as having no theory at all.
We are going to dive into how they magically unified those 5 theories, and trust me, it involves some of the most beautiful logic you will ever hear.
It really does.
But before we do, I want to take a brief moment to softly remind you that you are listening to a deep dive by Decoding the Dark.
Take a breath.
If you are finding a sense of calm in these cosmic mysteries, if your mind is enjoying floating through these hidden dimensions, please consider liking this video and subscribing to our channel. It helps us continue to bring you these gentle journeys into the unknown. Let the concepts wash over you. There's no test at the end, just the quiet awe of discovery.
The search for unity is deeply restful. To realize that apparent chaos is just a disguised form of order.
And in 1995, that search for order in string theory reached a profound turning point, known as the second superstring revolution.
Yes.
So, set the stage for us. It's the mid-90s. The math has yielded 5 distinct, highly complex superstring theories.
They were known by somewhat sterile mathematical names: type I, type IIA, type IIB, heterotico, and heterotici.
Right.
And they were, on the surface at least, completely different mathematical frameworks.
How different are we talking?
Very different. Type I, for example, contained both open strings and closed strings, and the strings were unoriented, meaning they didn't have a specific direction of flow.
Okay.
But type IIA and type IIB contained only closed strings. Furthermore, they handled the chirality, or the handedness, of particles differently.
What does that mean, handedness?
In our universe, certain particles spin in a specific direction relative to their momentum, like a left-handed screw versus a right-handed screw. Type IIA was non-chiral. It treated left and right equally. Type IIB was chiral. It allowed for fundamental asymmetries.
And the heterotic theories were even weirder, right? They were like a Frankenstein hybrid of the old 26-dimensional bosonic theory and the 10-dimensional superstring theory.
Exactly. They had strings where the vibrations moving to the left lived in 26 dimensions, and the vibrations moving to the right lived in 10 dimensions.
That sounds chaotic. It felt like physicists had spent decades climbing a grueling mathematical mountain, hoping to reach the single unified peak of reality, only to break through the clouds and find 5 separate, distinct peaks.
Which is incredibly frustrating. The whole point of a theory of everything is that there is only one of them.
Right. If you have 5 different versions of reality competing with each other, it suggests that maybe none of them are the true fundamental blueprint. Maybe they are just mathematical curiosities.
And the physics community was highly fractured over this. But then came the annual String Theory Conference at the University of Southern California in 1995.
And what happened there?
Edward Witten, who is widely considered one of the most brilliant mathematical physicists alive, stepped up to the podium and delivered an absolute masterstroke of synthesis.
What did he reveal?
Witten demonstrated that these 5 distinct theories were not actually competing theories at all. They were entirely consistent with each other.
Oh, wow.
They were just 5 different ways of looking at the exact same, deeper, underlying framework. He called this overarching framework M theory.
And the M stands for, well, it's a bit of a mystery itself, isn't it?
It is. Witten playfully suggested it could stand for magic, mystery, mother, or membrane, depending on your taste. He never officially defined it.
But the implications were earth-shattering. Witten showed that M theory seamlessly connected the 5 string theories through mathematical translation dictionaries known as dualities.
Yes, dualities.
Let's unpack these dualities,
Yeah.
because this is where reality starts to feel like a hall of mirrors. The 2 main ones are P-duality and S-duality.
Let's start with T-duality because it completely shatters our human intuition about size and distance.
Okay.
T-duality stands for target space duality. To understand it, let's go back to one of those hidden, compactified dimensions. Imagine taking one of those dimensions and curling it up into a simple circle with a specific radius. Let's call that radius r.
Okay, I am picturing a hidden dimensional circle of size r.
In string theory, a closed string, a little rubber band, can do 2 completely different things on this circular dimension. First, it can simply fly around the circle.
Like a race car on a track.
Yes. As it moves, it carries a certain amount of kinetic energy, which physicists call momentum modes. And the rules of quantum mechanics dictate that in a small space, momentum is quantized.
So the energy from moving around the circle.
Right. Second, because the string is a flexible, one-dimensional object, it can literally stretch and wrap itself entirely around the circular dimension, like a rubber band stretched tight around a cylinder.
Oh, I see.
This takes energy because the string has tension. We call this winding energy, or winding modes. A string can wrap around the circle once, twice, 100 times.
So the total energy of the string in this dimension is a combination of its momentum energy from moving and its winding energy from stretching.
Exactly. Now here is where the magic of T-duality happens. The mathematical formula for the momentum energy is proportional to 1 over r.
Okay, so as the circle gets smaller, the momentum energy goes up.
But the formula for the winding energy is proportional to r. As the circle gets bigger, the string has to stretch further, so the winding energy goes up.
They are perfect inverses of each other.
Yes. T-duality proves that if you take a universe with a very large compact dimension, a huge radius r, and you simply mathematically swap the momentum modes with the winding modes, the equations perfectly describe a universe with a very small compact dimension, a radius of 1 over r.
Hold on. You are saying that a universe where the hidden dimension is the size of the Milky Way galaxy is physically indistinguishable from a universe where the hidden dimension is smaller than a proton?
They are completely identical.
Wait, really?
Yes, the physics playing out in both universes is exactly the same. An observer inside that universe could not perform any experiment to tell you if they were living in the giant universe or the tiny universe.
That is mind-bending.
Under T-duality, type IIA string theory on a circle of radius r is mathematically equivalent to type IIB string theory on a circle of radius 1 over r.
So T-duality acts as a bridge. It shows that 2 seemingly different theories, operating at vastly different scales, are just the same physics described in 2 different mathematical languages.
Absolute size at the deepest quantum level is just an illusion.
That is profound. It completely destroys the concept of absolute geometry. If size is relative, what about S-duality?
S-duality, or strong-weak duality, connects the coupling constants of the theories. The string coupling constant, usually denoted as G sub s, determines how strongly strings interact with each other.
How fiercely they merge and split apart.
Right. When the coupling constant is very small, the interactions are weak.
Which is good for physicists, right?
Yeah.
Because weak interactions are easier to calculate.
Exactly. When interactions are weak, physicists use a technique called perturbation theory. They calculate the most basic interaction, then add tiny mathematical corrections for slightly more complex interactions, and so on.
It's an approximation, but it is highly accurate.
Yes. This is how the 5 theories were originally studied in the 1980s. They were studied in their weakly coupled states.
But when you turn up the dial, when the coupling constant gets strong, the interactions become chaotic.
Strings are merging and splitting constantly. The tiny mathematical corrections become massive, and perturbation theory completely fails. The math becomes impossible to solve.
But S-duality reveals a miracle. It proves that a string theory with a very strong coupling constant is mathematically identical to a different string theory with a very weak coupling constant.
Yes. For instance, strongly coupled type I string theory is exactly the same as weakly coupled heterodyco string theory.
So if a physicist is trying to solve a problem in type I and the coupling is too strong, they don't have to throw their hands up in defeat.
No, they just pull out the S-duality dictionary, translate the entire problem into the language of heterotico, solve it easily there because the coupling is weak, and then translate the answer back.
It provided a master key to unlock the strongly coupled regions of string theory that had been completely hidden in the dark.
Witten used these dualities to weave all 5 theories together into a single, cohesive web, but M-theory did something even more radical. It added an 11th dimension.
Right, here's where it gets really interesting. We just spent all this time agonizing over the mathematical necessity of exactly 10 dimensions.
The ghost fields demanded it. Supersymmetry demanded it.
Right, and now Witten says, actually, let's make it 11. Why?
It wasn't an arbitrary addition. It was a revelation hidden in the math of type IIA string theory.
How so?
As physicists used S-duality to crank up the coupling constant in type IIA, making the strings interact more and more strongly, something bizarre happened. The strings began to stretch, not in length, but in thickness. They gained a new dimension.
Oh, like drawing a thick line with a marker. If you draw it thin enough, it looks like a 1D line. But if you press hard and let the ink bleed, it thickens into a 2D ribbon.
Exactly. The one-dimensional string opened up. It became a 2-dimensional membrane living in an 11-dimensional spacetime.
Wow.
Witten showed that all the 10-dimensional string theories were actually just low-energy, weakly coupled, flattened shadows of this grander 11-dimensional M-theory.
And this is where M-theory introduces a whole new cast of fundamental characters. It's not just strings anymore, it's brains.
Yes, brains, short for membranes.
Right, we have one brains, which are the fundamental strings we've been talking about. But we also have two brains, which are 2-dimensional surfaces, like a sheet of paper.
We have 5 brains, and theoretically, p-brains of various dimensions up to 9. These brains are massive physical objects within the theory.
They aren't just background geometry. They have mass, energy, and tension.
Exactly. And this solves a huge structural problem regarding those open strings we talked about earlier.
Right, the open strings, the ones with endpoints, carry the forces of electromagnetism and the nuclear forces.
But if they have endpoints, what are they attached to? They can't just be dangling in the void?
They are attached to the brains. Specifically, a class of brains called Dirichlet brains, or D-brains.
Yes, the endpoints of an open string are mathematically glued to the surface of a D-brain.
So the string can slide around smoothly on the surface of the brain, like a puck gliding on an air hockey table. But it cannot detach and float away into the higher dimensional space.
It is anchored.
Which leads to what I think is the most mind-blowing cosmological implication of M-theory, brain cosmology. What if our entire universe, the vast 3-dimensional space containing all the galaxies, stars, and planets we can see, is just a giant 3-brain?
It is a profoundly compelling model. In this scenario, all the matter and light in our universe, the electrons in your body, the quarks in the Earth, the photons shining from the sun, are manifestations of open strings.
And because open strings are permanently tethered to the D-brain, all of that matter and light is physically trapped on this 3-dimensional surface.
We cannot see into the extra dimensions. We cannot move into the extra dimensions.
We are like characters painted on a canvas. We can move up and down, left and right across the painting, but we are completely unaware of the 3D art gallery the canvas is sitting in. We are confined to the surface.
But there is one crucial exception. Yes. Remember, the graviton is a closed string. It is a perfect loop. It has no endpoints. Therefore, it cannot be tethered to the D-brain.
So gravity is the only source that can detach from our universe and leak out into the higher dimensional bulk space.
Yes. And this beautifully, elegantly explains one of the greatest, most frustrating mysteries in all of physics, the hierarchy problem.
Why is gravity so incredibly, absurdly weak compared to the other fundamental forces?
Think about a tiny refrigerator magnet. That little piece of metal can pick up a paperclip, effortlessly defeating the gravitational pull of the entire planet Earth.
The entire mass of our planet is losing a tug of war against a tiny magnet. Why?
Because the magnetic force is made of open strings. It is trapped entirely on our brain. All of its strength is concentrated and confined to our 3 dimensions.
But gravity is made of closed strings. It is diluting itself, bleeding off our brain, and expanding out into the vast 11-dimensional void. We are only feeling a tiny residual fraction of its true strength.
Just floating on a membrane in an 11-dimensional void, feeling the faint echoes of gravity passing through us. It is a wonderfully humbling thought to let settle in your mind.
It really is.
Yeah.
But M-theory, as vast and magnificent as it is gave birth to a mathematical concept that suggests our reality might be something else entirely, something almost paradoxical.
Yeah.
We need to talk about the holographic universe.
Yes. This is a term that gets thrown around a lot in pop science, and it usually evokes images of sci-fi projections. People hear hologram and they think of a glowing blue, flickering image of a person floating in the air.
Right. But in physics, we are talking about a strict mathematical principle of information. Think of a can of soup. A literal, physical aluminum can of soup sitting in your pantry.
Okay.
Now imagine that every single piece of information about the 3D soup inside that can, the exact position of every carrot cube, the temperature of every water droplet, the velocity of every sodium ion, is perfectly mathematically encoded on the two-dimensional flat paper label wrapped around the outside of the can.
That is an excellent visualization. The label doesn't just describe the soup. The mathematics on the label actually projects or generates the reality of the soup inside.
The holographic principle, championed by physicists like Gerard Hooft and Leonard Susskind, emerged from the study of black holes.
It posits that all the information contained in any three-dimensional volume of space can be fully and completely described by a theory that operates solely on the two-dimensional boundary of that space.
The 3D volume is fully described by the 2D boundary.
Yes, and for years this was just a compelling philosophical idea. But in 1997, a brilliant physicist named Juan Maldacena found the first concrete, rigorous mathematical realization of this principle using string theory.
It is called the anti-de Sitter conformal field theory correspondence, or 8SCFT for short.
Malacena's paper on this discovery has become the most highly cited article in the entire history of high-energy physics. It changed everything.
So let's break down the 8SCFT correspondence.
Yay.
Let's map it to our soup can analogy. What is the soup and what is the label? Let's start with the soup. What is anti-de Sitter space?
The soup is a fully fleshed out theory of quantum gravity, specifically a string theory, operating inside a specific type of curved, five-dimensional space called anti-de Sitter space, or ADS space.
Anti-de Sitter space is not like the flat space we experience,
Yeah.
right? It has a negative cosmological constant, meaning it has a constant negative curvature.
Like a saddle shape, yes, a hyperbolic geometry.
Okay.
If you have ever seen the famous artwork by M.C. Escher called Circle Limit, where angels and demons are tessellated inside a circle, getting infinitely smaller and more densely packed as they reach the outer edge, that is a 2D representation of anti-de Sitter space.
It acts almost like a fishbowl. It has a definitive boundary at infinity, and if you threw a particle toward that edge, the curvature of space would reflect it back to the center.
Okay, so we have a five-dimensional hyperbolic fishbowl, and inside this bowl we have the full complex machinery of string theory, vibrating strings, D-branes, and crucially, gravity.
That is the bulk, that is the soup. Now, what is the label? What is the conformal field theory, the CFT?
The label is a conformal field theory living purely on the four-dimensional boundary of that 5D fishbowl.
A conformal field theory is a very specific type of quantum field theory. It is scale invariant, meaning the physics looks exactly the same whether you zoom in with a microscope or zoom out with a telescope.
There are no fundamental markers of size or distance, and most importantly, this boundary theory does not contain gravity. It is a flat, standard quantum field theory.
Specifically, Maldacena used a highly symmetrical theory called n-porous supersymmetric Yang-Mills theory.
So, to summarize, we have a 5D space with gravity inside the bowl and a 4D space without gravity painted on the flat surface of the bowl.
And Maldacena's monumental breakthrough was proving that these two theories, despite operating in different dimensions and despite one having gravity and the other lacking it completely, are exactly mathematically equivalent.
They are an exact dual to each other. Every single particle, every force, every dynamic interaction happening in the 5D gravitational bulk has an exact corresponding mathematical counterpart happening in the 4D quantum boundary.
It is a perfect translation dictionary between two completely alien languages.
Yeah.
But why is this so useful? Why is this considered the holy grail of modern theoretical physics?
It relies on that strong-weak duality we talked about earlier.
Right.
And that is why it is an absolute superpower for physicists. Remember S-duality. When the quantum particles on the boundary are interacting so fiercely and strongly that the math becomes impossible to solve, a strongly coupled state, the ADI-SCFT dictionary translates that impossible scenario into the 5D bulk.
And in the 5D bulk, the strings and gravity are interacting very weakly.
Exactly. And weakly interacting gravity is just Einstein's classical general relativity, which we know how to calculate perfectly. It's just smooth curves and geometry.
That is genius. You take an unsolvable, chaotic quantum math problem on the flat boundary. You translate it into a solvable, elegant geometry problem in the 5D bulk. You solve it using the smooth curves of gravity and black holes, and then you translate the answer back to the boundary.
Physicists have used this exact method to study real-world physics that has nothing to do with string theory. For example, they use the 5D gravity of AD-SCFT to understand the behavior of quark-gluon plasmas, which are incredibly hot, strongly coupled fluids that existed just microseconds after the Big Bang.
That is wild. They're using hypothetical 5-dimensional black holes to solve the math of actual real-world particle collisions happening in accelerators on Earth.
But AD-SCFT also finally solved a massive paradox regarding black holes themselves: the entropy problem.
Yes, for decades there was a deep tension between Stephen Hawking's macroscopic description of a black hole and the microscopic rules of quantum mechanics.
In the 1970s, Jacob Bekenstein and Stephen Hawking proved that a black hole has entropy. Entropy is essentially a measure of hidden information, the number of possible microscopic states of a system that look identical from the outside.
And the mind-blowing part of their discovery was that a black hole's entropy is proportional to the surface area of its event horizon, not its total volume.
Which itself is a massive clue hinting at the holographic principle. The information of the 3D volume of the black hole is encoded on the 2D surface area of its horizon.
Exactly. But there was a problem. Standard physics could calculate the macroscopic formula for this entropy, but it couldn't actually count the microscopic bits of quantum information inside the black hole to verify it.
Standard physics broke down at the singularity. But using the framework related to AD-SCFT, physicists Andrew Strominger and Kamran Vafa were finally able to count the bits.
How did they do it without falling into the infinity trap?
They constructed a mathematical model of a black hole in string theory using a specific arrangement of intersecting D-branes. They then used the holographic dictionary to translate this black hole into a weakly interacting quantum gas of open strings on the boundary.
Clever.
Because the strings were weakly interacting on the boundary, they could simply count the microscopic quantum states. They counted the vibrations of the strings.
And when they added up all the quantum states on the boundary, did it match the Bekenstein-Hawking formula for the black hole in the bulk?
It matched perfectly, down to the exact numerical factor. It was a massive triumph for string theory. It proved that string theory could successfully resolve the deepest paradoxes of quantum gravity.
If we connect this to the bigger picture, well, what does this actually mean for reality? For the listener lying in bed right now, looking up at the ceiling.
It implies that space itself and the force of gravity might not be fundamental ingredients of reality.
Wow.
In the AD-SCFT correspondence, the extra dimension of the bulk space, the depth of the fishbowl, literally emerges from the quantum entanglement of the particles on the lower dimensional boundary.
Space-time might just be a holographic illusion, a macroscopic projection generated by microscopic quantum information interacting on a distant, flat surface.
It's like looking at a 3D video game on a monitor. The 3D world you are running through, the mountains you climb in the game, the gravity that pulls your character down, none of it is real space.
It is an emergent property created by 2D lines of code running on a flat silicon computer chip.
If the holographic principle holds true for our universe, the 3D space we feel ourselves moving through right now might just be the physical manifestation of quantum code processing on the boundary of the cosmos.
It is a profound, paradigm-shifting way to perceive existence. We are the projection. But as elegant and mathematically airtight as this tapestry is, string theory has a problem.
A deep philosophical and mathematical crisis that emerged as physicists realized just how vast and flexible this theory truly is. We have to talk about the landscape.
Right, because if string theory is the ultimate theory of everything, it should naturally predict the exact universe we live in. It should produce one unique solution.
It should spit out the exact mass of an electron, the exact strength of gravity, the exact density of the dark energy that is expanding our universe. But it doesn't do that, does it?
No, it doesn't. And the reason comes back to those extra 6 dimensions we discussed earlier, the Calabi-Yau manifolds, the microscopic geometry hidden in the bedsheet.
To get the physics of our everyday 4D universe from the 10D mathematics of string theory, you have to compactify the extra 6 dimensions. You have to fold them up.
Yes, but the equations of string theory don't tell you which specific Calabi-Yau shape to use. And it turns out there isn't just one way to fold up 6 dimensions.
There are many ways. And furthermore, you can wrap different configurations of energy called magnetic fluxes around the various holes and loops inside these microscopic spaces.
So how many possible ways are there to configure these hidden dimensions?
By the early 2000s, physicists like Michael Douglas, Schmidt-Cottreau, and Leonard Susskind calculated the possibilities. They realized that the number of stable or metastable compactifications is staggeringly huge. The widely quoted mathematical estimate is 10 to the power of 500.
That's a 1 followed by 500 zeros. To put that into perspective for the listener, the total number of atoms in the entire observable universe is only about 10 to the power of 80.
10 to the 500 is a number so incomprehensibly massive that human language fails to capture it.
Yes. And each one of those 10 to the 500 configurations represents a specific vacuum state. And each vacuum state corresponds to a completely different possible universe with different physical constants, different particles, different masses, and different forces.
This vast, infinite collection of possibilities is called the string landscape.
I have to push back here and express some genuine frustration. Hold on. You're telling me there are 10 to the 500 possible universes predicted by this theory?
Yes.
At that point, aren't we just doing philosophy?
Yes.
How can we even call this a scientific theory if it predicts literally everything?
It's a fair point.
If you can just tweak the dimensions, adjust the magnetic fluxes, and fine-tune the geometry to fit any possible observation we make with our telescopes, then the theory has zero predictive power. It becomes unfalsifiable.
It is a very sharp, very valid critique, and it caused deep, bitter divisions within the physics community. Some physicists embraced the landscape. They coupled it with the anthropic principle and the idea of a multiverse.
The idea that our universe is just one tiny bubble in an infinite foaming sea of universes, and all those 10 to the 500 possibilities actually exist out there in the void.
Exactly. And the anthropic principle states that we shouldn't be surprised that our specific universe has the exact, finely tuned physical laws necessary to allow carbon-based life, stars, and galaxies to evolve.
Because if the laws were even slightly different, if the electron was a little heavier or gravity a little stronger, life wouldn't exist and no one would be here to ask the question.
We just happen to live in the one bubble out of 10 to the 500 that allows for our existence.
I understand the logic of that. It's mathematically sound. But it feels like a massive cop-out for a physicist looking for a fundamental equation. It feels like throwing your hands in the air and saying, well, things are the way they are because if they weren't, we wouldn't be here.
That doesn't tell me why the electron weighs what it does.
Exactly.
Many leading physicists shared your frustration, and that is why Kamran Vafa, a prominent string theorist at Harvard, introduced a powerful, rigorous counterprogram. He sought to constrain this infinite chaos. He introduced the concept of the swampland.
The swampland. I love the imagery. The landscape of viable, healthy universes surrounded by a muddy, impossible, toxic swampland.
It is an evocative name. Vafa argued that just because you can sit down with a piece of paper and write out a consistent-looking, low-energy quantum field theory doesn't mean that theory can actually exist in reality.
The swampland is the infinite sea of mathematically logical quantum field theories that cannot be successfully combined with a quantum theory of gravity.
So they look perfectly fine at low energies, but when you try to zoom in, when you try to integrate them into a complete high-energy UV-completed theory of quantum gravity like string theory, they break down. The math falls apart.
They are fundamentally inconsistent with gravity. Vafa is suggesting that gravity acts as a strict, unyielding cosmic bouncer. It rejects the vast majority of conceivable universes.
Vafa and his colleagues proposed a set of strict swampland conjectures, rules that any physical theory must obey to be part of the true landscape and not sink into the swampland.
And if these conjectures are true, the landscape of actual physically viable string theories might not be 10 to the 500. It might be much, much smaller. A tiny island surrounded by an infinite swamp. What are some of these rules? Because if they are true, they are basically the fundamental constitutional laws governing the creation of reality.
One of the most famous and rigorously tested is the weak gravity conjecture.
What does that dictate?
It states that in any consistent theory of quantum gravity, gravity must always fundamentally be the weakest force. Specifically, in any universe, there must always exist at least one particle whose electrical or gauge charge is vastly stronger than its mass in Planck units.
So the force pushing two particles apart electrically has to be stronger than the gravitational force pulling them together.
Precisely. We see this in our own universe clearly. If you take two electrons, they have mass, so gravity tries to pull them together. But they also have a negative electric charge, so electromagnetism tries to push them apart.
The electromagnetic force repelling them is roughly 10 to the power of 40 times stronger than the gravitational force pulling them together. gravity is pathetically weak.
But why is that a rule? Why couldn't a universe exist where gravity is the strongest force?
To understand why, we have to look at black holes again. Black holes evaporate over time through a process called Hawking radiation. They slowly leak energy back into the universe and shrink.
Now, imagine a universe where gravity was the strongest force. If an electron's mass was greater than its charge, you could form a black hole out of pure electrons. This black hole would have an immense electric charge.
Okay, a highly charged black hole.
As this black hole evaporates, it loses mass. But to get rid of its charge, it has to spit out charged particles. If the particles in this universe are heavier than they are charged, the black hole would lose more mass than charge.
Eventually, it would shrink down to a microscopic state where its mass is too low to contain its massive electric charge.
The physics would break. It would become a naked singularity, violating the laws of thermodynamics.
It would leave behind an infinite number of microscopic, highly charged remnants, which breaks the fundamental laws of quantum mechanics regarding entropy and information bounds.
Therefore, to allow black holes to evaporate cleanly and smoothly without breaking the universe, there must exist a particle whose charge is greater than its mass. Gravity must be the weakest force.
Any hypothetical universe where gravity is strong sinks immediately into the swampland. It cannot exist.
That is absolutely fascinating. It takes an observation about our universe that gravity is weak, and instead of just shrugging it off, it proves it as a fundamental mathematical necessity for existence. What's another swampland rule?
The no global symmetries rule. In standard quantum field theory, you can have global symmetries, which lead to conservation laws. For example, the conservation of baryon number, which ensures the number of protons and neutrons remains stable.
But the swampland dictates that in a universe governed by quantum gravity, there can be no exact global symmetries.
Why does gravity hate global symmetries?
Once again, black holes act as the ultimate theoretical laboratories. If you throw a dictionary into a black hole, the black hole doesn't care about the text, or the language, or the baryon number of the pages.
According to Stephen Hawking, a black hole is only sensitive to gauge charges, mass, electric charge, and angular momentum. Everything else is ignored.
So the black hole eats the global symmetry.
And when the black hole eventually evaporates, it radiates its energy blindly, randomly. It does not spit back out the conserved baryon number. The global charge is permanently destroyed by the evaporation process, which violates the supposed symmetry.
Therefore, consistent quantum gravity flatly forbids exact global symmetries. All symmetries must be gauge symmetries, like electromagnetism, which have a specific force particle associated with them that the black hole can detect and conserve.
It really feels like black holes are the ultimate stress test for reality. If a mathematical theory breaks inside a black hole, it belongs in the swampland.
They are the boundaries of our understanding.
Yeah.
And these swampland conjectures are incredibly important because they are bringing a sense of order and discipline back to string theory.
They are providing testable constraints, pulling the theory back from the edge of untestable philosophy and grounding it in severe, rigorous physical restrictions.
Which is incredibly reassuring. Now, we've spent a lot of time down in the microscopic depths looking at strings at the Planck length and discussing theoretical constraints on unseen dimensions.
But I want to shift our gaze upward. I want to transition to the macro scale, because the ultimate test of any theory is observation. Can we actually see any of this?
If string theory is real, if these fundamental strings exist, did they leave a signature in the cosmos that we can detect with our telescopes today?
That is where this deep dive takes us to one of the most exciting dynamic areas of modern observational cosmology: cosmic strings.
Okay. To understand cosmic strings, let's use an analogy. Imagine a glass of water slowly freezing into an ice cube. When water is liquid, it is highly symmetrical. It looks the same in every direction.
But as it freezes, it undergoes a phase transition. The water molecules lock into a rigid crystal lattice, but it rarely freezes perfectly clear.
The ice crystals start growing from different points in the glass, and when these different crystal domains meet, they don't always align perfectly. They form flaws, fractures. You see those white, cloudy cracks running through the center of a solid ice cube.
That is a brilliant physical analogy. According to modern cosmology, right after the Big Bang, the universe was unimaginably hot. It was a single, unified state where all the forces of nature acted as one superforce.
It was highly symmetrical, like liquid water. But as the universe rapidly expanded, it cooled. And as it cooled, it went through violent phase transitions, much like water freezing into ice.
The symmetry broke. The forces of nature, gravity, electromagnetism, the nuclear forces, separated from one another, freezing into the distinct forces we see today.
And just like the ice cube, the vacuum of space-time didn't freeze perfectly smoothly everywhere. Where different expanding domains of the new, cooled vacuum met, they formed physical flaws.
The topology of the vacuum itself fractured. These fractures are one-dimensional topological defects. They are infinitely thin lines of concentrated primordial energy left over from the birth of the universe. We call them cosmic strings.
Now I have to clarify something because the terminology gets confusing. Are these macroscopic cosmic strings the exact same thing as the microscopic fundamental superstrings of string theory that make up electrons?
Historically, they were thought to be two completely different, unrelated phenomena. Cosmic strings were first predicted by standard quantum field theory in the 1970s, envisioned by physicist Tom Kibble. They were macroscopic phenomenological defects.
Superstrings were the tiny building blocks of quantum matter. But in the early 2000s, string theorists like Joseph Polchinski and Henry Tai had a realization that merged the two concepts.
What did they realize? How do you connect a microscopic string to a macroscopic galaxy-spanning fracture?
The connection is cosmic inflation. During the earliest fractions of a second of the universe, there was a period of rapid exponential expansion. Space itself stretched faster than the speed of light.
If fundamental strings, or D strings from M theory, were present in the universe during this inflationary epoch, the violent expansion of space would have grabbed hold of them. It would have stretched them to intergalactic proportions.
A microscopic fundamental string, normally the size of the Planck length, could be stretched until it spans the entire observable universe.
A stretched fundamental string. A literal microscopic thread woven into the macroscopic tapestry of the galaxies. That is almost poetic.
They are known as cosmic superstrings. And because of the warped geometry of the extra dimensions in those flux compactifications we discussed, these superstrings can have a much lower tension or energy density than the old-school field theory cosmic strings.
They would be incredibly long, infinitely thin, and staggeringly heavy. A single piece of a cosmic string the length of a football field might weigh as much as the entire planet Earth.
And what are they doing right now? Are they just out there floating statically in the void between galaxies?
They are not static at all. They are highly dynamic. As the universe continues to expand, this network of cosmic strings is constantly moving, interacting with itself. Because they are under such immense tension, they whip around through the cosmos at a significant fraction of the speed of light.
Like massive intergalactic bullwhips.
And when a string crosses over itself, or collides with another string, the math shows that they can reconnect. They snap, swap ends, and pinch off. If a string crosses itself, it can pinch off a closed loop of string that separates from the main network.
Like tying a knot and snipping the ends, leaving a free-floating hula hoop of cosmic string.
Yes. And these loops are unstable. They are under immense tension, so they oscillate and vibrate violently. As they wobble and whip around over billions of years, they slowly lose energy. They decay.
But they don't fade away silently. They radiate that lost energy outward primarily in the form of gravitational waves.
Gravitational waves, ripples in the actual fabric of space-time itself, which, thanks to modern technology, we are finally able to detect.
Exactly. This is where high-level string theory meets experimental reality. We now have massive, incredibly sensitive observatories like LIGO on Earth and the upcoming space-based observatory LISA.
When a cosmic string loop oscillates, or when a sharp kink or cusp on the string snaps at the speed of light, it emits a powerful, highly specific burst of gravitational radiation.
A literal snap of a cosmic bullwhip, sending a ripple through space that washes over the Earth.
If the density of these cosmic superstrings in our universe is high enough, and if they tend to cluster in the gravitational wells of galaxies like dark matter, LIGO or LISA could potentially detect these distinct gravitational wave bursts.
The signal would have a specific mathematical signature, entirely unlike the gravitational waves produced by colliding black holes or merging neutron stars.
It would be direct, observational, irrefutable evidence of a fundamental string. What else are we looking for? Are there optical ways to see them?
Yes, through a phenomenon called optical microlensing. Because a cosmic string is so unbelievably massive, its intense gravity dramatically warps the fabric of space around it.
Like placing a heavy lead pipe on a soft mattress, the fabric pulls inward.
Exactly. So imagine a long, straight cosmic string happens to drift perfectly between our telescopes on Earth and a distant, bright background star or quasar. The warped space around the string acts like a lens.
It bends the light of the star as it travels toward us. But unlike a normal spherical lens, like a magnifying glass that might distort or magnify an image, the specific conical space-time geometry created by a cosmic string produces a very specific, striking optical illusion.
It cuts the image in half and bends both sides around the string, creating two perfectly identical unmagnified images of the background star.
So an astronomer would look through a telescope and see a single star suddenly split into two perfect clones separated by a tiny angle and eventually merge back together as the string drifted past in the night sky.
Precisely. We have not definitively detected a cosmic string yet, either through gravitational wave bursts or through optical microlensing. There have been false alarms, but no confirmed sightings.
However, the search is highly active, and if we ever find one, it provides a direct experimental window into the earliest, hottest moments of the universe.
It would be the ultimate proof that the macroscopic cosmos is deeply, fundamentally connected to the microscopic quantum realm of string theory.
It is truly breathtaking to consider. The idea that a microscopic vibration, the very note that gives an electron its mass, could be stretched across the void of space, whipping at the speed of light, bending the light of ancient stars, and sending ripples through the fabric of time.
It brings such a profound sense of scale and interconnectedness to the universe. It connects the absolute smallest building blocks of reality to the absolute largest structures in the cosmos. It unites the quantum world with the grand architecture of gravity.
And as we gently bring this journey to a close, I want to ask you, the listener, to just reflect on your place in this grand architecture.
It's important to ground it all.
Why should you care about 11 dimensions, or vibrating strings, or holographic boundaries, or cosmic bullwhips? Because understanding that the deepest layers of reality are interconnected brings a profound sense of peace.
The chaos of everyday life, the stress of your routine, the noise of the world, it is all underpinned by a majestic, rhythmic, cosmic symphony.
Everything from the light of the sun to the cells in your body is vibrating in perfect mathematical harmony. You are made of the exact same notes as the distant galaxies.
We are all woven from the same fundamental threads, resonating in the hidden architecture of the hidden dimensions.
So what does this all mean? We started this deep dive by looking at the night sky, expecting it to be made of solid little billiard balls, and realizing that when you zoom in far enough, the microscope of physics shatters.
Reality is not made of solid, unyielding dots. It's a continuous, flowing symphony of strings, vibrating in a 10-dimensional space, anchored to membranes, floating in an 11-dimensional bulk.
And if we take that one step further, leaning into the holographic principle we explored, I'll leave you with this final provocative thought to mull over as you drift off to sleep.
If the ADA-CFT correspondence is the true blueprint of reality, and the three-dimensional space we walk through is truly just a holographic projection emerging from quantum entanglement on a distant, lower-dimensional boundary, what happens if the entanglement on that boundary changes?
Oh, that is a staggering thought.
Is our entire experience of moving through physical space, and perhaps even our perception of the flow of time itself, just a beautiful, persistent illusion? Are we simply experiencing the sensation of quantum information reorganizing itself on a flat surface at the absolute edge of the universe?
An illusion of space, generated by the deep quantum code of the cosmos. That is a stunning thought to fall asleep to. I want to thank you for taking this deep dive with us.
It's been wonderful.
Once again, you have been listening to a production by Decoding the Dark. If this journey brought you peace, if it expanded your mind as you drift off, please leave a like and subscribe to help our channel grow.
Thank you for listening.
We wish you a peaceful, deep, and truly restful sleep as your mind floats effortlessly through the 11 dimensions. Good night.